Hello. Today we'll be discussing some concepts from Chapter 14 of Maxfield and Babbie. Chapter 14 is all about interpreting data. So up until this point, we've learned about various ways to conduct a research study. We've discussed how to select independent and dependent variables, how to select the research design, sampling, collecting data. Now we're going to talk about how we would actually interpret and analyze the data that we've collected for a study. So empirical research usually utilizes some type of statistical analysis, and that's what we will be discussing in this chapter. I realize that math and statistics can be overwhelming and anxiety inducing, but what we're going to do here is just break it down and make it simple, and we'll walk through some examples. And remember that empirical research is actually based more on logic than on math. Math is just simply the best way to demonstrate the logical operations that are inherent in a good data analysis. So really this is more of a logical exercise than a mathematical exercise. So hopefully that helps alleviate some of your anxiety. Anyway, there's two basic types of statistics in criminology and criminal justice research: descriptive statistics and inferential statistics. Descriptive statistics are used to summarize and otherwise describe data in manageable forms. Okay. Inferential statistics help researchers form conclusions from their observations, and forming conclusions usually about a population from which a sample was drawn. So if you think about Chapter 8, we talked about sampling and how we might use probability sampling to draw a sample from some larger target population and then use the findings of that sample to speak for that larger target population. That's all inferential statistics are. They allow us to infer from that sample to that target population, whereas descriptive statistics basically just describe the characteristics of a variable or the relationships that we might expect to see among multiple variables. So we'll talk a little bit about describing variables here using descriptive statistics. So the simplest statistics describe some type of average or dispersion for a single variable. All right, descriptive statistics represent a method for presenting quantitative descriptions in a manageable form. So if we start with one variable and describing the characteristics of that variable, that is the univariate level of description. So uni meaning one. So if we're talking about a single variable, that is a univariate description. If we add a variable to this discussion, and now we're talking about two variables and possibly the relationship between these two variables, now we're talking about a bivariate description. Okay, and if you think about the root here, the root of the word bi means two. So you're probably familiar with some other examples of the use of the word or the use of the root bi in other language. So if we think about someone that's bilingual, for instance, bilingual means they speak two languages. If we talk about sexuality, someone that's bisexual, it means they're attracted to both sexes. Bivariate just simply means we're talking about two variables. All right. If we add a third variable to the mix, now we're talking about a multivariate relationship. So multivariate describes three or more variables. Okay, so this is pretty easy stuff. When we're describing the characteristics of a variable, just remember univariate, we're only talking about one variable. Bivariate, we're talking about two variables. Multivariate, we're talking about three or more variables. So we'll talk a little bit now about data distributions. Okay, data distributions are a way to display univariate data. And the book gives this example of the ages of a number of judges. So let's say that we went to a courthouse and we collected data on the judges in that courthouse and how old they were. And so here's an example of some of the age data that we might find. So one judge is 63, one judge is 57 years old, one judge is 49, one judge is 62, and so on and so forth. Okay, now one way that we could display this data is we could display it in raw form as I have it here, so we could just list the ages of all the judges in this court. However, that can get pretty cumbersome, and you know, a lot of people are not going to read that, and they're not really going to understand it. And imagine if we have a very large data set, say we had 100 cases, we have the ages of 100 judges. Obviously, it wouldn't be feasible to list every single age. So one way that we might do that is we might list it in what's called a frequency distribution, where we report things in terms of percentages. And so we lose some detail, but it's easier to read and understand. So here is an example of a frequency distribution as it would apply to those ages of judges, okay? So what I've done is I've listed here the age categories, okay? So we have under 35, 36 to 45, 46 to 55, 56 to 65, and 65 and older, all right? And then I've just simply taken the percentage of judges that fall into each strata. So for instance, 9% of our judges are under 35. 21% of our judges fall between the ages of 36 and 45 years old. 45% of our judges are between 46 and 55. Now I have some additional categories here, so you'll always want to put the total, okay, and make sure that that totals out to 100%. And we have the number of cases here, 433. So basically, we have 433 judges and their ages that are represented by the data here, all right? And we also have some additional categories for no data. So these are cases where maybe, you know, we know that there's a judge, but we don't know how old they are, right? So maybe just the courthouse didn't have data on these judges, or maybe if we were surveying them, they didn't write their age in. So there's 18 judges that we don't have any data on. So you'll always want to report the total, and also if there's any cases where you don't have data or missing data, all right? But this is just an easier way of displaying the data. So again, if we had ages of 433 judges, wouldn't make sense to list all those ages individually. We could display them in a frequency distribution like this. Okay, so it's you know, pretty straightforward. And again, we lose some detail here, but it's a lot more manageable. So we can also kind of cross-compare. So we can say that, for example, that the least number of judges are 65 and older, because we know that 6% of our judges fall into that category. And then we also see less judges in the under 35 category, which I think that makes sense logically, because, you know, in order to become a judge, you have to have a number of years experience, you know, with the bar, and you know, and then you have to get elected and so forth. So we don't see too many young judges. And also we know a lot of judges tend to retire, so I think that's probably why we don't see a lot of older judges. But most of our judges fall between the ages of 46 and 55. All right, that's the largest category at 45%. So this is just kind of the story that, that this data tells us. All right, we'll talk a little bit about the measures of central tendency, or summary statistics. So this is basically a measure of the clustering of observations as they pertain to the midpoint of the distribution, all right? And there are three basic measures. So the mode, the mean, and the median. The mode is just simply the value that occurs most frequently. The mean is the average of all the values. Okay, and to define the mean, you basically add up all the values and then divide by the total number that are there. The median is the middle value. So this is what cuts the distribution in half. So half of our values are going to be above the median and half are below it. And in order to calculate this, you put all the values in order and then select whatever's in the middle that cuts that distribution in half. And so to really kind of understand this, we'll walk through some examples now. So we'll talk about the mode. So again, the mode is just the most frequent attribute. So in a data distribution, the mode is just going to be that observation that we see the most frequently. All right. So I have an example here. Let's just say that we collected data on the ages of juvenile offenders in a detention facility. And so each observation represents the age of a juvenile offender. So here we have a person that's 12 years old. Here we have someone that's 15. Here we have someone that's 14, and so on down the line. So in order to determine the mode, really all we do is we just kind of look at these numbers and we just see which one occurs most frequently. Okay, so you can just eyeball it, or you could go ahead. Probably an easy way to do it would be to just put the numbers in rank order and then just see how many times you have specific observations. So here I've already determined that the mode is 16 because we see 16 approximately 3 times. So we have 12, 15, 14, 13, 15, 14. Here's someone that's 16. Here's someone that's 16. Here's 12, 13. Here's another person that's 16. So we have 3 individuals that are 16 in this data set. 16 is the age that we see the most, and so the mode is 16. All right. Let's assume now that we have some data on adult offenders in a correctional facility. So again, if we want to determine the mode, it's just going to be the observation that we see the most. So we can eyeball these numbers and we see that the mode is 22 because we have 2 individuals that are 22. Okay, and we don't see any other ages that are repeated here. All right. So again, the mode, pretty easy. It's just the attribute that we see the most. And just, we don't see this example here, but sometimes it is possible to have more than one mode. So, you may have 2 modes. If you have 2 modes, it's called a bimodal distribution. If you have 3 modes, it's called a trimodal distribution. All right. In these cases, though, we only had 1 mode in each. So this is a unimodal distribution. All right, we'll talk a little bit about the mean. So the mean is basically just a fancy word for the average. So it's the sum of the values of all the observations divided by the total number of observations. Okay. So again, if we have the ages of a number of juveniles in detention, what we can do is simply add up all these ages and derive a total, and then we divide that by the number of observations or the number of cases that we have. Okay, so we'll go ahead and just walk through this calculation. I know the answer is already here, but let's just go ahead and verify that it is in fact correct. All right, so again, these are just the ages of juveniles in detention. So we have someone that's 12, we've got someone that's 15, we've got someone that's 14, we've got someone that's 13, we've got another 15-year-old, okay, we've got a 14-year-old, we've got a 16-year-old, we've got another 16-year-old, we've got a 12-year-old, and we've got a 13-year-old. Okay. And, yep, it totals out to be 140. So the first step in calculating the mean, you want to always add up basically the observations that you have. And then you want to take 140, or take your total here, and divide by the total number of observations. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations. So we're going to divide by 10. And the mean, or the average age of the juveniles in this data set, is 14. All right, so pretty simple. Let's go ahead and calculate the mean for our adult offenders. I've already done it for you. You can see the mean is 28, but let's just go ahead and verify that. So once again, we're just going to add up. These are the ages of our adult offenders. So we have someone that's 18. We've got a 37-year-old, a 23-year-old, a 22-year-old, a 25-year-old, a 43-year-old, a 19-year-old, a 50-year-old, a 21-year-old, and a 22-year-old. So we add that up and we get 280. We know there's 10 observations, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to divide by 10. And that tells us the mean age is 28. All right. So again, the mean, calculating the mean, is just figuring out the average. Okay. So you add everything up, then you divide by the total number of observations. All right. Talk a little bit now about the median. So the median is just simply the middle attribute in a rank order distribution. So it's the midpoint, the middle, that just cuts that distribution right in half. So when you find the median, half the values should be below it and half should be above it. Okay, so to calculate the median, the first thing you'll want to do is rank order all the observations in your data set. So put them in number order. So again, if we have that list of the ages of juvenile offenders, we'll go ahead and put them in order first. Okay, and then we want to search for the number that's going to cut the distribution in half. So I've already determined the answer here, but it's going to be 14. Why is it 14? Because it cuts the distribution in half. You have 1, 2, 3, 4, 5 observations basically below, and then you have 1, 2, 3, 4, 5 observations above. So this cuts the distribution exactly in half. All right, so that's pretty simple. Now here's where things get a little more complicated. So if you have an odd number of observations, it's very easy to find the median. Okay. However, if you have an even number of cases, it's a little more difficult because it doesn't cut the distribution exactly in half. Okay. So the calculations are a little more complicated. Basically, what you would do is you go ahead and rank order the numbers first. Okay, so again, here's our ages of our adult offenders now. So I've used this before. So we've got our adult offenders. Okay, what we do to determine the median is we rank order them. So we put them in numeric order here. All right, and then what we do is we find the two numbers that cut the distribution exactly in half. Okay, so it looks like it's going to be probably this 22 and 23, because we have then 1, 2, 3, 4, 1, 2, 3, 4 observations on either side. So we take the two numbers, and then what we do is find the mean, or the average, of those two numbers. So we have a 22 and 23. So to find the mean, remember, we just add the two observations together and then divide by the total. In this case, we're only interested in 2, so we'll divide that in half, and then the median is 22.5. All right. You only need to go through those calculations if you have an even number of cases. If you have an odd number of cases, it's pretty easy. You just take the middle number that cuts the distribution in half. Even number of cases, take the two middle numbers and then find the mean, and then that's your median. All right. So talk a little bit about the measures of dispersion. The measures of dispersion are the distribution of values around some central value, such as the mean. Okay. We have to be careful about calculations that involve the mean, because the mean is affected by very large and very small numbers. Okay. So we might want to calculate measures of dispersion. All right, and this will tell us a little bit more about the data. So the two major measures of dispersion are the range and the standard deviation. The range is simply the distance that separates the highest value from the lowest value. And the standard deviation is the amount of variation about the mean itself, or the average amount that each individual observation varies from the mean. Okay, so I'll provide some examples of this in just a second here. So first let's talk about the range. So the range, as I mentioned, it's the distance that separates the highest from the lowest value. Okay, so again, we'll go back to our example of the age of juvenile offenders in detention. All right, so the range is going to be the distance between our highest value, or the highest age, and the lowest value, or the lowest age. Okay, and so to calculate it, what you could do is rank order the numbers as I've done here, or you can eyeball it and just look for the smallest and largest numbers, but it's probably better just to rank order it. So go ahead and put them in rank order. So again, we've got our scrambled ages here. Here they are rank ordered. The largest number is 16 and the smallest number is 12. So we've got someone that's 16 years old. The youngest person we have is 12. Okay, so in order to figure out the distance between 12 and 16, or the range, we just calculate it out. So we take our largest number, which is 16, and then we subtract the smallest number, and we get 4. So the range is 4. Okay, so the range, pretty easy to calculate. Just take the largest number, subtract the smallest number, and that's the range. All right, the standard deviation is a little bit more complicated. This is the average amount that each individual observation varies from the mean. So in other words, we have the mean of our distribution, and the standard deviation tells us that the amount that each individual observation varies from that mean. Okay, so we have a lot of observations that will be exactly on the mean, but then we have some that might be above the mean or below the mean. And the standard deviation just tells us the amount that those observations vary. All right. The calculations for this are pretty complex. There's a good example of the calculations on page 401 of Maxfield and Babbie. I'm not going to walk through them because they're pretty complicated. And actually, one of the great things about statistical analysis is that software will do the calculations for you. So if you have SPSS or Stata and you're doing some sort of analysis, it'll calculate the standard deviation for you, as well as really everything else that I've just talked about. So I'm not going to walk through the standard deviation calculations, but I'll just kind of explain briefly how the standard deviation can be helpful. So let's assume that we've calculated the standard deviation for the juvenile age data and also the standard deviation for the adult age data. So the standard deviation for the juveniles is 1.41. The standard deviation for the adults is 10.61. Okay, so on its own, if we just looked at that standard deviation of 1.41, it doesn't really mean anything. The standard deviation is good when it comes to comparing data sets. So we can see that if we look at the adult data set and compare it to the juvenile data set, the standard deviation for adults is a lot larger, 10.61. So what that means is that there's a lot more variation on those observations around the mean in the adult data set. Whereas in the juvenile data set, there's really not a whole lot of variation around the mean. I mean, because the standard deviation is 1.41. So what this tells us is that there's more variation for adults. Why do you think that is? I'll pose the question to you. Why would we see more variation in adult age versus juvenile age? Well, the answer is actually pretty simple. So if we think about the ages of juveniles, the age range is basically 1 through 18, or or 1 through 17, because once you're 18 years old, the law considers you as an adult. Okay, and if we think about adult ages, the age range could be anywhere from 18 basically on up to, let's say 100 years old, right? Anyone, over the age of 18 is considered an adult. So in these two, comparing these two data sets with our ages of juvenile offenders and our ages of adult offenders, we would expect to see more variation with our adult offenders, right? Because basically we could have anyone over 18 is considered an adult. However, but basically to be considered a juvenile, you have to be under 18, so there's less variation there. So we would expect to see a larger standard deviation for adults as compared to juveniles, and in this case we do. We see a standard deviation of 10.61 for the adults compared to our juveniles at 1.41. All right, so basically that kind of wraps it up for the discussion. If you have any questions at all about the descriptive statistics that we just talked about, please send me an email or leave me a comment here on YouTube, and I would be happy to address it. And yeah, that pretty much wraps it up. Thanks for your attention.